Hello everyone! In this video, I'm going to explain some of the structures of formal math, including definitions, conjectures, proofs, theorems, lemmas, corollaries, and axioms. And I'm going to use the story of two kitties and one alien to do it. This is probably the goofiest video I've ever made, so hope you enjoy it. Alright, so when I think about myself as a mathematician, I imagine that I'm in a sandbox, and I am the ruler of the sandbox. So I get to make up my own definitions, my own laws, whatever I say goes in my sandbox. Okay, so let's look at an example. I can make up a definition for something called a Curfupal. A Curfupal is a number whose digits are in ascending order. For example, 1, 2, 3, they go up, or 4, 5, 8, 9. Okay, well that's all well and good, but what if I want to invite a friend to play with me in this sandbox? They're probably going to have some questions if they're anything like me. For example, they might want to know about repeated digits. Does 1, 1, 2, 2, 3, 3 count as a Curfupal? Does 4, 5, 5, 8, 9, 9, 9 count? Are those kinds of things Curfupals? So at that point, you realize that you need to revise your definition to be more specific, more unambiguous. Okay, so you could revise it like this. A Curfupal is any number such that each digit is strictly less than the digit on its right. So for example, in 4, 6, 8, 9, 4 is less than 6, 6 is less than 8, 8 is less than 9. So every digit is less than the one on its right, and they can't be equal. Okay, so that might satisfy your friend for a while, but at some point they might decide to get a little more inquisitive and ask what you even mean by a digit. Like, are we definitely talking about the regular decimal representation of numbers? Are we allowed to use binary, decimal, hexadecimal? So if you haven't studied binary or like hexadecimal notation yet, this slide might not make that much sense to you. But basically there are other ways to write numbers aside from just using the symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. For example, in the binary system, you can write any number with just the symbols 0 and 1. And in the hexadecimal system, you can write any number using the symbols 0 through 9, and then also A, B, C, D, E, F. So if we allowed other systems like binary or hexadecimal, that would completely break the definition of the Curfupal. So we have to be specific and say that we're talking about numbers represented in decimal form, and decimal form means using the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can revise our definition again to be like this. So a Curfupal is any number such that when it is written in decimal form, each digit is strictly less than the digit on its right. And again, if your friend is a mathematician, they may continue to have questions. So if they really get picky, then they might say, well, you're talking about every digit is strictly less than the digit on its right. But when you're looking at the rightmost digit, the last digit in a number, there is no digit to the right of that. So what does it mean when you say that each digit is strictly less than the digit on its right? So at that point, you really might get annoyed and you revise your definition again. Like this. A Curfupal is any number such that when it is written in decimal form, each digit except the rightmost digit is strictly less than the digit on its right. So this definition keeps getting longer and more complicated as your friend is pointing out more and more problems with it. And now here's another one. So what about decimals? We just said numbers, right? Did we mean integers, or are we letting decimals be Curfupals? Like, is 123.456, is that a Curfupal? Okay, so at this point you might feel really defeated, but you do have to say what you mean, right? Otherwise people won't understand. So let's say a Curfupal is any real number, which includes decimals, such that when it is written in decimal form, each digit is, except the rightmost digit, is strictly less than the digit on its right. Okay, so maybe your friend accepts that, but actually this introduces a lot of problems because what could happen is, what if people put extra zeros at the end? Like sometimes people do this when they're writing decimals, right? If they stick a bunch of extra zeros at the end, then something that looked like a Curfupal initially might no longer look like one. All right, like 1.23, that's in order, but 1.23000, now it's not in ascending order anymore. And also, what about zeros at the beginning? Are we not going to let those be Curfupals either? And then you have the even additional problem, which the second kitty here didn't mention, but sometimes people put a 0 before the decimal and sometimes they don't. So how would we deal with that? Okay, so at this point, our original little gray kitty over here has completely given up on dealing with this decimal problem and is going to change his mind and just make these be integers. Okay, so a Curfupal is any integer such that when it is written in decimal form, each digit except for the rightmost digit is strictly less than the digit on its right. Okay, so that solves a lot of the problems with the definition. And second kitty is like, well, why didn't you just say so? So this is a common problem in math, that your definitions need to be unambiguous. They need to be written very carefully. But other than that, you really can define anything that you want in a definition. A definition is just a declaration that you're going to call a certain thing by a certain name, and you get to make up the name. Of course, there are a lot of things out there already that other people already made up the names for, but there are certainly infinitely many things that you could still define yourself and make up the name for, like a Curfupal, if you're feeling silly. But you do have to be careful about how you word them, and this is really why in math textbooks you see a lot of really complicated definitions with a lot of very particular words in them, and every single one of those words is important, because if you take any of them out, suddenly the definition becomes ambiguous and people can't tell exactly what you mean by it. Okay, so that's why definitions are typically pretty long and complicated, and that can also make them a little tricky to understand sometimes. So here's our final definition of a Curfupal. It's any integer such that when it is written in decimal form, each digit except for the rightmost digit is strictly less than the digit on its right. So kind of complicated, but with this definition, you can definitely tell whether any integer is a Curfupal or not. Okay, so once you've got some definitions, then you can play with them. So let's say you're playing in your sandbox. Well, someday it might occur to you, you might have the idea that, those Curfupals, I think there are only finitely many of them. And perhaps you have a disagreement with on this with your friend. Maybe they think there should be infinitely many. So how are you going to settle this argument? Are there finitely many or infinitely many? So this brings us to conjectures. A conjecture is a statement that you think might be true, and they usually refer to previously defined terms and also axioms. I'll tell you what axioms are later. So here's a conjecture. There are only finitely many Curfupals. Conjecture 1. So once you have a conjecture, you want to try to prove it. Otherwise, no one's going to believe you. So how would we prove this? All right, so maybe one idea of how we could prove it would be if we could show that there was a biggest and a smallest Curfupal, then there would have to be only finitely many of them. That's just a property of the integers. In between any two integers, there can only be finitely many integers. Like, for example, between negative 1,000 and 1,000, there's only finitely many integers. So that would be one way you could try to prove this. And if you think about it for a while, you can probably figure out that 1, 2, 3, 4, 5, 6, 7, 8, 9 would have to be the biggest Curfupal. Can you think of any that are bigger than that? So that would have to be the biggest one, but that in itself is not that easy to prove. So that's a second conjecture. The greatest Curfupal is 1, 2, 3, 4, 5, 6, 7, 8, 9. So how would you actually go about proving that? If you were trying to convince someone who was skeptical that there's no bigger Curfupal than that, how would you convince them? Well, a first attempt might be something to do with the fact that that you can't have any more digits than 9 in any Curfupal. So the most digits that a Curfupal can have is 9, right? So if there was a bigger Curfupal than 1, 2, 3, 4, 5, 6, 7, 8, 9, if there was one bigger than that, it would have to have 9 or more digits, but it can only have 9 digits, so it would have to have 9 digits. And then from there, the digits have to be in order, so that goes most of the way towards a convincing proof. So the reason you can't have more than 9 digits in a Curfuple is because you can't have repeated digits, right? If they're repeated, then that breaks the definition of each digit being strictly less than the one on its right. And you also can't have 0 as a digit. If you think about that for a while, I hope you'll realize why that's true. You can't have 0, except for 0 itself. That is a Curfuple. But any other number cannot have 0 in there because 0 would have to go in the far left position in order to be less than the other digits. But we don't write numbers with 0 in the far left position. Well, we don't write integers like that anyway, except for 0 itself. Okay, so at this point, likely just knowing that all Curfupals have 9 or fewer digits, that already tells you that there's only finitely many of them. Because there's only finitely many integers that have 9 or fewer digits. You can count all of them yourself, right? Like you can start at 0, 1, 2, 3, and go up through, what would it be? 999,999,999? That's the positive ones. And then the negative ones, you can count those too. So that already is enough information to say that there's only finitely many Curfupals. All right, so once you've figured out this kind of chain of logic here, you basically just need to write it down in order to get other people to follow it. And this is what most of formal mathematics is writing things down really clearly, really unambiguously, so that other people can follow what you were thinking. So there's a couple of more structures here that are useful when you're doing that. Proofs, theorems, and lemmas. So a proof is a logically correct argument that a statement is true, and a proof is based on definitions, axioms, and theorems. Again, I'll tell you what axioms are later, but they're similar to definitions. A theorem is a statement that has been proven. So basically, when you're writing a proof, you can use things that other people have already proved to save you time. And then a lemma is just a type of theorem. It's a theorem that's not very interesting or important by itself, but it acts as a stepping stone to proving something interesting or important. And what is a lemma is completely in the eye of the beholder. One person's lemma could be another person's theorem, or one person's theorem could be another person's lemma. So it's not really an important distinction, but you will see lemmas a lot in textbooks, so that's what those are. All right, so let's look at a couple of examples here based on this Curfupal nonsense. So here's lemma 1, and I'm calling it lemma 1 because it's the first one in this particular document. So lemma 1, the only Curfupal that has 0 as a digit when written in decimal form is 0. So proof of this, how will we convince anyone that this is true? Well, see if this convinces you. Since the digits of a Curfupal in decimal form are strictly increasing from left to right, the only possible position for a 0 digit would be the leftmost place, leftmost digit. But in decimal form, the only integer with 0 in the leftmost place is 0 itself. So we would consider an integer with 0 in the leftmost place other than 0, that would not be proper decimal form. That's just not the way we write integers usually. All right, so if you're convinced by that, then we can use that to prove theorem 1. Again, it's theorem 1 because it's the first theorem in this document. All Curfupals have 9 or fewer digits when written in decimal form. So see if this argument convinces you. Since the digits of a Curfupal in decimal form have to be strictly increasing from left to right, there cannot be any repeated digits. From lemma 1, we know that we cannot use 0 in a Curfupal. So here, that's an example of using a previously proved theorem. So we cannot use 0, so a Curfupal can only use the digits 1 through 9. Well, since we can only use 1 through 9 and we can't repeat them, well, there must be at most 9 digits in a Curfupal. Hopefully that's pretty straightforward logic there. All right, so now that we know what a lemma and a theorem are, let's keep going. Right, so at that point, once you realize that there can only be 9 digits at most in a Curfupal, it actually becomes pretty obvious that there's only finitely many of these Curfupals, because like I was saying before, there's only finitely many integers that have 9 or fewer digits. Okay, so this brings us to a corollary. A corollary is a theorem whose proof becomes obvious immediately after another theorem is proven. So in this case, right after we prove theorem 1, it really becomes obvious that there's only finitely many Curfupals. And in some cases, it might be so obvious that the author who's writing down the corollary might not even write down the proof of the corollary. Sometimes they do. If they do, it's usually short, like one sentence. So in this one, corollary 1, there are only finitely many Curfupals, and the proof this is an immediate consequence of theorem 1. So what is actually obvious? Again, this really depends on the author and who they think is going to be reading their work. So something that's obvious to like other professional mathematicians might not be obvious to students. So typically in a textbook for students, you would see a lot longer and more detailed of proofs. Okay, so we talked about definitions, theorems, proofs, corollaries, lemmas. So what else is there? Well, there's axioms. So how are we going to get to axioms? Let's say we're playing in the sandbox again one day, making some definitions, some proofs, some theorems, conjectures, and a new friend appears. Here's our new friend. This friend is a little bit strange looking, I think. I'm not sure if they're a cat or a jelly or what are they exactly. Maybe they're from another planet. This one is from Jupiter. And is there math on Jupiter? I don't know. This is a matter of philosophy, whether math exists only because of humans or whether it sort of exists independently of humans. Our alien friend here seems to think it's universal. So let's say you try to tell your new friend about the Curfupals and give them your definition. Well, they might have some more questions than you originally had. Like, for example, if you look at that definition, let's look back at it for a second. There's a whole bunch of words in that definition that we didn't define, right? Like there's integer, there's decimal form, there's digit, less than, right? We didn't define any of those things. We just assumed that the reader knew what those were. But what if they don't? What if they don't know? So how could we possibly tell them what an integer is, for example? It's a pretty shocking situation to be in. But sometime around the 1800s, late 1800s, people started kind of wondering this, like maybe we should be more clear about what we mean by these really basic things like integers. So I guess the most obvious way to define an integer would be, it's those numbers that you use to keep track of how many things you have, like the fingers on your hand or, your pencils or whatever it is that you count in those first grade math books like oranges and apples and stuff. But maybe that's not such a great definition for someone from Jupiter. Maybe they don't have oranges and apples, although I guess they have pencils, at least in this picture. So what if they don't let you define it that way, or they sort of reject that definition? Then how on earth would you define an integer? You'd have to just sort of start describing everything that defines integers. Well, what does it define an integer? I mean, okay, if they don't know like the symbols for them and you can't convince them by holding up numbers of apples, you could say, well, the integers are their things. You can add and subtract them. You could give them examples of that. They each have a positive and a negative version. When you add the positive version to the negative version, you get 0. 0 is special because when you add or subtract that to another integer, it doesn't do anything. The value of the other one stays the same. You could just sort of start trying to list off these kinds of facts about integers and kind of hope they get the idea. Now look carefully at these facts that I've listed here, though. These don't only apply to integers. They actually also apply to real numbers, right? So now you've got to think about, well, what does make the integers special? Like, why are they different from other numbers? So you'd have to throw in some other notions to distinguish between the integers and the real numbers. And the most important thing that distinguishes the integers from the real numbers, of course, is when you put the integers in order from least to greatest. And we actually talked about this earlier, right, when we were showing the Curfupals were finite. Between any two integers, when you've got them lined up in order, there can only be a finite number of other integers. But that's different from the real numbers. Of course, between any two real numbers, there's an infinite number of other real numbers. So that distinguishes the integers and the real numbers. But of course, that's only the integers, and it wasn't even a very good definition that I just gave there. There's plenty of other questions that our little alien friend might have, like, what do you mean by lining them up in order from least to greatest? What does that mean? So you can really keep going deeper and deeper and try to ask what each word in each definition means. And at some point, you can't go any deeper. And at that point, you've reached the level of axioms. Or the level of crying, like our little kitty friend here. So what is an axiom? So an axiom is a property that we declare to be true about a certain kind of object in order to define how those objects behave. So axioms, they're kind of the same as definitions, except that they define behavior instead of just terminology. So they don't just say that you're going to use a word to mean a certain thing. They say that these things that you've defined, they're going to behave a certain way. So for example, here are some of the axioms that define the integers. The integers would not be the integers as you know them if any of these things were missing. So the operation of addition on the integers satisfies the following. If you have any two integers, let's call them a and b, then a plus b is a uniquely defined integer. In other words, a plus b, if you know what a and b are, you always get the same thing when you add a and b. You never like suddenly get something different one day. Like 2 plus 3 is always 5, it's never 7. That's what uniquely means there. For any integers a and b, a plus b is the same as b plus a, so addition is commutative. For any integers a, b, and c, if we do a plus b first and then we add c, that's the same as doing b plus c first and then adding a. So that means addition is associative. The integer 0 satisfies 0 plus a is the same as a, and that's the same as a plus 0. And then for any integer a, there exists a negative version of a called negative a, such that negative a plus a is 0. So those are some of the axioms of addition on the integers. And then they also have an ordering that satisfies the following. For any two integers a and b, exactly one of the following is true. Either a is less than b, or a is greater than b, or a equals b. So only one and exactly one of those can be true for any two integers. And then another thing about the ordering is that for any two integers a and c, such that a is less than c, there are only finitely many integers b, such that a is less than b is less than c. So for example, if a is 10 and c is 20, then for b we could have 11, 12, 13, 14, 15, 16, 17, 18, 19, and that's a finite list of only 9 integers that can go in the middle. So there are more axioms for the integers, but these are some of the most basic ones, and I hope you get the idea of what an axiom is from this. So the thing about axioms that makes them different from theorems is that axioms do not need to be proved, and in fact they can't be proved. We assume axioms are true in order to give us something to do math with. Just like with definitions. Definitions give us something to do math with. It's something to play with in the sandbox. So axioms are the tools that we use to prove other things. You don't need to prove them, and in fact you can't prove them. So this means something a little bit strange that you might never have thought about before, but this does mean that every theorem you've ever encountered, from the Pythagorean theorem to the fundamental theorem of calculus, all of those were proved by a mathematician who was assuming, without proof, that certain axioms are true. So what exactly were they assuming? And should you be sort of aware of those, or does it matter? I mean, the ones about integer arithmetic certainly didn't seem very controversial. None of these are like objectionable ideas here, even though we can't prove them. But what exactly do other mathematicians assume are true? So let's go back to our kitties here. So little gray kitty here is kind of freaking out and questioning whether math is all built on a foundation of lies. Well, yeah, I mean, not exactly, but kind of. So his friend is teasing him here. So axioms, they're not lies. I mean, you can't prove them, but they're not lies. They're assumptions about what kind of sandbox we're playing in. So those assumptions that we make about the integers, let's look back at them again for a second. All of these assumptions are coming from the fact that integers are meant to model collections of objects in the real world, right? Like if I have 3 apples and then I get another 2 apples and I put them in the same pile together to get 5 apples, that's addition, right? And it doesn't matter which apples I put in the pile first. And that's why we say that addition is commutative, because when you're just piling things together, it doesn't matter which ones you pile on first. So these axioms here, they come from the fact that we're trying to model things in the real world. And so, yeah, none of the assumptions that mathematicians, or the axioms that mathematicians use are particularly objectionable, but they are assumptions that we can't prove. So that does mean that that all of our theorems that we've proved over the centuries and the millennia are only true if our assumptions are true. Okay, so almost all mathematicians use the set of assumptions or the set of axioms called ZFC. That stands for Zermelo-Fraenkel set theory plus axiom of choice. So I showed you that set of axioms for the integers, but actually you can derive all of those ones for the integers from ZFC. Even though ZFC is strictly about sets and not about integers, you can derive the integers from sets. So yeah, Zermelo-Fraenkel set theory plus axiom of choice. If you want to read all of the axioms that are in there, you can just Google it and read the Wikipedia article. So all of the math you've done to this point in your life has been founded in ZFC. All of the theorems that you know are only true if the axioms of ZFC are assumed to be true. So yeah, that might be a little kind of shocking, but that's how it is. So there are 9 axioms in ZFC, and most of them are like totally normal, totally non-controversial, like obvious things that you would agree with. For example, the first one is 2 sets are the same set if they have the same elements. Seems pretty obviously true, right? But the thing is that we can't prove this because if you take this away, then we have nothing to prove it with. It's something that's so fundamental that you can't prove it because it is the basis on which the rest of math rests. There have been in the past some kind of controversies about ZFC, but like for example, there was almost a century-long argument about whether to include the axiom of choice. And of course, Gödel, uber famous guy from the 20th century, early 20th century, he proved that every consistent system of axioms cannot be used to prove its own consistency. So there have been some interesting and perhaps alarming developments along those lines, but you know, don't you want to play in the sandbox? If you want to do math with the rest of us, you have to get in this ZFC sandbox. Well, of course you don't have to, you know. I mean, you can make your own sandbox, you can make your own axioms, you can throw out the axiom of choice if you want to. Maybe you should know what it is before you throw it out, though. So what is the axiom of choice, actually? So the axiom of choice, it kind of gives you like some rad infinity superpowers. I'll just try to explain it in an informal manner. So basically it says that given any collection of bins, each one containing at least one object, it is possible to make a selection of exactly one object from each bin, even if the collection is infinite. So the bins are basically sets. And if you think about this, I mean, if it was a real world situation, you couldn't do that because you'd run out of time and you'd die of old age before you got done selecting. But in math, we don't really think of things as taking any time. We can just do them. So that's kind of a superpower in that sense. Yeah, so that is the axiom of choice. And I did indeed copy and paste that from Wikipedia. Wikipedia has lots of good math information. So anyway, the axiom of choice is also logically equivalent to the well-ordering theorem, which we will actually study a little bit in this class. So the well-ordering theorem says that every set can be ordered in such a way that each non-empty subset has a least element. So if that totally did not go in just now, what that means is basically, like, for example, the positive integers, you can order them from 1, 2, 3, 4, 5, 6, 7, 8, just the regular ordering. And then if you take any non-empty subset, for example, 3, 5, 8, 9, that would have a least element. So in this case, the least element would be 3. And any non-empty subset, like 4, 5, 6, 17, whatever, would have a least element. So for that example, it would be 4. Okay, so when you think about it for the positive integers, it's not a very hard thing to see. But actually, if you start thinking about this, so well-ordering theorem says that every set can be ordered in that way. So for positive integers, it's like, okay, yeah, I can see what the ordering would be that would make that true. But what about the set of all integers? It actually becomes a little bit hard to see as soon as you include the negative integers. Because if you just take all of the integers, then the negative integers are a subset of that, but they don't have a least element. There's no least negative integer. There's only negative infinity, but negative infinity is not an integer. So yeah, you can't use the regular ordering on the integers to show that the well-ordering theorem is true for the integers. You have to make up like some weird, creative, kind of off-the-wall other ordering that works. So yeah, that is the well-ordering theorem, and we will use it a little bit in this class. But like I said, if you don't like the axiom of choice and you don't like the ZFC axiom system, you can totally make your own sandbox and you can play in it. There won't be very many people playing in there with you, but in math, it's like the kingdom of imagination, you know? You can make whatever you want. You can make your own sandbox, your own definitions, your own axioms, your own conjectures, your own theorems, your own proofs. It's all up to you. I just wanted you to know about some of these formal structures, what some of these things mean, like definitions, axioms, theorems, proofs, and yeah, hope you like this goofy little video. If you have any questions, let me know.